Hey everyone, how are you? Good to see you. You guys just saw me switch into the screen, which is how I go and make sure that the background is working. So that's why you saw the white background. I also just found out that there's a sound going on. Let's hit this. Okay, great. Okay, well, welcome back. Happy Monday to everybody. It's interesting to be able to have this opportunity to continue to talk about math with this whole audience. I hope that you had a very good weekend, and I hope you had a restful Sunday. I had the opportunity to talk to a bunch of you on Saturday night, and on Saturday night we answered all kinds of questions that had to do with maybe learning math or thinking about math or maybe even helping someone else in your family to learn math. But on the weekday live streams, what I do is I like to go and talk about some actual math problems. If you're new to these live streams, what we do is we will always be trying to talk about some question that you might raise. I'll be choosing to talk about topics which are in the Algebra 1 to Geometry level, although you'll often see that I'll pick a question that might look like it has nothing to do with Algebra 1 or Geometry, only because I think that there's something there that I can talk about that might be interesting and understandable to people of this particular math experience level. Now, we will also be very intentionally trying to find questions that are not that normal. And the reason is because you're lucky enough that you already have teachers who can teach you mathematics that you might find in the school book. On the other hand, what I aim to show you here is what you might not be able to find in that school book, which is like a free-ranging discussion across all kinds of different mathematics topics. If you have been here before, you will notice that sometimes the way I'm picking on these questions is that I've been systematically trying to find questions that hopefully will be still interesting even if you've been watching for many, many sessions. So I will be trying not to repeat any particular ones of them. Okay. All right. So let's go ahead and get started. What kind of math questions do we have today? So I'm looking at all of the different sources that I have for your different questions. Let's see. What do we have here? I see that there's... Oh, how is formula found besides finding a pattern, says Lauren's son. Oh, that's interesting. So you're asking how someone might find a formula besides just trying to find a pattern. How might I do that? Maybe I can give you an example. This one might be useful. Okay, so let's talk about finding a formula, and I'll use something which is something that maybe I discovered when I was an algebra student. Maybe some of you discovered this when you were an algebra student also. I'm going to write down a sequence of numbers, okay? And see if you can tell me what number goes next. One moment, please. I'm thinking of the sequence of numbers. Okay, great. So here's the first number, 2. The second number is 10. The third number is 30. The fourth number is 68. And the fifth number is 130. What's next? How do you figure out questions like this? So I gave you a sequence, 2, 10, 30, 68, 130. What would you do? The fun thing about doing a live stream is that people can also write things in the live chat. So I'm actually quite curious what people would do if you saw a sequence like this. 2, 10, 30, 68, 130. What is what you do? Addition. That's a good idea. So let's try some addition. If you want to go and say, somebody's wondering, is the answer 260? We'll find out soon. But somebody's trying to say, let's try some addition. So what do you mean by addition? Would you try to say, like, let's add up all these numbers? Factors? Factors is a good try. Let's try that. Let's try a few of these. So addition, you try to add some numbers. It's not completely clear to me what you would do in terms of addition. On the other hand, I can do factors. What do factors tell me? Factors tell me 2. 2 times 5. 6 times 5, which is 2 times 3 times 5. So far, so good. It looks like some nice small factors. But then, all of a sudden, 68, what's that? 2 times 34. 34 is 2 times 17. Yuck. And this is 13 times 10. 2 times 5 is 10 times 13. So factors, I don't really know. Factors might be a little bit hard. I'm not sure about the factors. I see a lot of different kinds of answers which are popping here. I also see that there's a lot of people who seem to like writing 2. Like 2, 2, 2. Wonder why. Now, a lot of people think it's 2 to 2. We don't know why. Let's go and find out. So now if we want to go and figure this out, the factors thing didn't help too much. It was a good idea to go and try. I see that a dolphin has said yuck as well. But like that doesn't seem to work. Let's try something else instead of addition. Let's try subtraction. That's in fact what I did when I found this sort of stuff the first time when I was doing this in middle school. Somebody asked, what is happening? What is happening is, what's the next number? Maybe I should write a question mark. So now we're not going to do now we're not going to do this particular idea. We're not going to try to factorize. We're not going to try to factorize. Instead, let's try subtraction. So what might you do with what might you do with subtraction? So with subtraction, what you could do is you could go and say, well, between the 2 and the 10, it went by 8. And between the 10 and the 30, it went by 20. And between the 30 and the 68, it went by 38. And between 68 and 130, it went by something. 62, maybe? Hopefully, 62. So is there a nice pattern here? What's the question, Aaron Peng asks. The question is, what's that number right there? 2, 10, 30, 68, 130, and then what? Right? And the question, second common difference. Someone says, let's go and take a second common difference and go and see what else there might be. So the second common difference is, this would be 12, this would be 18, and this would be, oh, look at that. Now, does anyone see what's going on? So this is exciting. Look, I did this common differences, and I found I got 12, 18, 24. Does anyone like 12, 18, 24? Yes. The third common difference is 6, says temp ID. That means that this is a 6, and this is a 6. Right? And so if that's the case, then I can go and figure out what should be next. I should take another 6. 24 plus 6 is 30. 62 plus 30 is 92. And now I can tell what this is. 130 plus 92. Aha. Ding, ding, ding. 222. So we have 222 as the answer, and that turns out to be what it was. Now the question was, how do you find a formula other than just like trying to find a pattern? I saw some people here actually had put a formula also. I saw that somebody had put a formula that is something cubed plus something. Somebody said it's like n cubed plus n. That's exactly what I did. So what I did is I did n cubed plus n. 2 was 1 cubed plus 1. That was 2. 10 was 2 cubed, which is 8, plus 2. You see it works? This was 3 cubed, which is 27, plus 3. And this is 4 cubed, 64, plus 4. 5 cubed, 125, plus 5 is 130. And 6 cubed, plus 6, that was the 222. That was the 222. So this is indeed the formula. The formula is actually I take the n cubed plus n. Now, the question was, how might you try to find these kinds of formulas? Somebody called this Newton's little formula. Indeed, this is an idea of, it's related to Newton and his work with calculus. It turns out that if your sequence has it so that at the third common difference is where it becomes all constant, then the sequence is going to be something which is what we call a polynomial of degree 3. What that means is it's made of stuff like up to n's, n squareds, and n cubes combined in some way. So the fact that this stabilizes at the 666 means that you actually can get something that looks like this. And in fact, if you look at other kinds of sequences, there's a question of why. That's a good question. I like your question, Eric. Let me show it to you like this, okay? Like, why might it be that a third degree sequence stabilizes at the third step? Well, let's do it this way. Let me start by talking about a first degree sequence, okay? What happens if I look at a sequence which is just like the nth term is, let's use something simple, 3n minus 2. Why not? We could do that. So if I want to do 3n minus 2, look. So if I have the nth term is 3n minus 2, I guess let's make a chart. Here's n, and here is the nth term. 3n minus 2. 3 times 1 minus 2 is 1. 3 times 2 is 6, minus 2 is 4. 3 times 3 is 9, minus 2 is 7. 3 times 4 is 12, minus 2 is 10, and so on. Okay? And now what are these common differences? If I go and look at the common differences, all of these common differences are 3. Now, can anyone tell me why it makes sense? Why does it make sense that those should all be 3s? why should all those be 3's? If this is 3n minus 2, why should those all be 3's? So here I'm just saying like the nth term is 3n minus 2. So why should the difference between the nth term and the n minus first term, yes, David Jiang, thank you, it's up by 3 for each n. And the way you can think of this is that what this 3 here is this is sort of like the difference between the n plus first term and the nth term. So if I'm taking the n plus first term minus the nth term, then that should give me this 3 here. And what happens if I try to put n plus 1 into that? Well, if the nth term is 3n minus 2, the n plus first term, I guess it shouldn't be called the n plus 1th, it's the n plus first term is 3 times n plus 1 minus 2. And what happens if I try to subtract them? Well, look, if I go expand the 3 times n plus 1 minus 2, whoops. If I go and try to expand the 3 times n plus 1 minus 2, that's 3n plus 3 minus 2, which is 3n plus 1. Although I actually have an easier way. I don't want to do it that way. I want to say, if I just want to subtract them, that would be more confusing. Expanding it out is worse. If I want to subtract them, and I want to subtract to see what the difference is, when I go from the lower to the bigger, then the difference is 3 times n plus 1 minus 2 minus 3 times n minus 2. And that's just going to be equal to, if I look at the 3's, I've got n plus 1 3's minus n 3's, and so that's just 1 3 left. And the minus 2 and minus the minus 2, those cancel. So in fact, I have n plus 1 3's minus n 3's is just 3, so this makes sense. So 3 is the common difference, says Paperboy. Thank you very much. That's very useful. But now let's go one more step. The next step is, hey, I've got a new sequence for you. This new sequence is where the nth term is, let's do 2n squared plus n. Why not? Let's try that. And let's take a look at what this looks like. Nth term. When n is 1, then the 2 times n squared plus n is 2 times 1 plus 2, which is 3. I hope that's right. Please correct me if there's a mistake. Ah, you're late. What are we talking about? We're talking about the interesting patterns that you find if you take differences from a pattern that looks like this. So just watch and you'll see something interesting. We're going to draw out a table which has all of these, these are all of the numbers which are 2 times n squared plus n. And if n equals 2, 2 times n squared plus n is 2 times 4 plus 2. What does that? Help me. Is it 10? I hope it's 10. It might not be 10. All of these arithmetics are hard for me. Okay? So if n equals 3, yes, Paperboy says I said your name, and I just said it again. Okay, so anyway, 2 times 9 is 18. 18 plus 3 is 21. Please correct me if I'm wrong. 4. 2 times 4 squared. 4 squared is 16. 2 times 16 is 32. 32 plus 4 is 36. Let's do one more. 2 times 5 squared. 5 squared is 25. Times by 2 is 50. Plus a 5 is 55. Okay, now I want to go and start taking these differences. From 3 to 10 is by plus 7. From 10 to 21 is by plus 11. From 21 to 36 is by plus 15. And from 36 to 55 is plus 19. I think there's a nice pattern. Look, that gives me this pattern. And if I look at what happens next, those are all differences of 4's. So look, I have something which is quadratic. It's like something which is n is up to the power 2. And it's that at this second layer is when they all became constant. Okay? But why? The reason why is just think of it this way. If the nth term is 2n squared plus n, what's the n plus first term? Let's write like this. That looks kind of... previously I did n plus 1 dash st. Now I'm putting the st on top. The n plus first term is 2 times n plus 1 whole thing squared plus n plus 1. Now watch, something interesting will happen. Suppose I subtract these. I see that somebody here knows calculus. So Tiger Lee, you said something with some D's. I think that means that you know some math that maybe some people here don't. But don't worry, we don't need any of that. But by the way, if you do know calculus, that is exactly what's going on here. And if you don't know calculus, don't worry, you don't need to. Just watch. If I take the top line minus the bottom line, what do I get? I have 2 times n plus 1 whole thing squared plus the n plus 1, and I'm going to write it this way, minus 2n squared minus n. Okay, now let's look at what happens like term by term. But not just term by term, I mean like this part and then that part. My answer of the difference is going to be putting these together. But let's do them one at a time. What happens here? So in this particular zone, I'll get something, and in this zone I'll get something. The second zone is easier. N plus 1 minus n, that's just 1. Okay? How about the first zone? I need to do 2 times n plus 1 whole thing squared minus 2n squared. Maybe I need some scratch work for that. What is n plus 1 whole thing squared? So n plus 1 whole thing squared is when you expand out this way. This is equal to n squared, and then there's an n multiplied by 1 and a 1 multiplied by n. There's 2 of them, so that's 2n, and then there's 1. Okay, and there happens to be a 2 in front. So in fact, what I'll do there is I'll say that this part is 2 times square bracket n plus 1 squared minus n squared. And then of course there will be this 1 from there. Okay, now let's finish. What happens here? If I expand out that n plus 1 whole thing squared and minus an n squared, oh, that's equal to just 2 times 2n plus 1 and then plus 1. The important thing is that this n squared subtracted away that n squared. And what I want you to take away from this is, look, the yellow number is what's going on in the first difference. And the yellow number has no more n squared in it. The important thing is I started with an n squared, and then what happens when you do one step of taking differences is it doesn't become an n squared anymore. It becomes 1 degree less. It became an n. And that's why this sequence of yellow numbers is what we call linear. This sequence of white numbers was quadratic. It was things involving n squareds. This is things involving only up to n's. And this is things involving only like no n's at all. It's constant. So that's why this works. The reason it works is because if I ever take an n plus 1 whole thing squared minus an n squared, the n squared term cancels away. And all I have left is the n term. So you lose 1 degree, so to speak. And what we did with the n cubed example that I started with, that's why it's 3 layers. In fact, the second layer after you do an n cubed sequence is just an n squared sequence. And after you do one more layer, you get an n sequence. And one more layer after that, you get a constant sequence. That's why it works. Okay, so that was an interesting question. I hope that this gave you an interesting tour. And in fact, you'll even get some things that have something to do with calculus someday around this too. Let's see. What other questions can we talk about? Okay, so I see an interesting question. This is by XX Ben Yang XXXX, lots of X's. And this says, how do people calculate how much gas they need to go around the F1 2019 track exactly once? Please choose me. I've watched you since your first video, but I've never been chosen, so I'll choose you, okay? So thanks, by the way, for watching ever since the first video. And now the question is how to figure out how much gas it takes to go around the whole F1 track. So I actually don't know what an F1 track looks like. I'm going to guess it looks like this. And please correct me if I'm wrong. So let's pretend that that's this F1 track. And you want to know how much gas you're going to use as you go all the way around. Now, this is a very interesting question because this is related to something in physics. You see, in physics, there's an important mechanical law, which is like once an object is in motion, it actually wants to stay in motion unless there's some force that's slowing it down. Oh, that's wrong. So this is not an F1 track? Maybe F1 track is something else. Or maybe people are talking about a different topic when they say that's wrong. I'm going to just pretend the track looks like this, okay? So the question is somehow, oh, F1. F1 is Formula 1. Sorry, not the F1 keyboard key. So the point is there's like some Formula 1 racing, and so people drive cars as fast as they can to go around a track. So now something very interesting here is that there is this Newton's law, and Newton's first law is that the object in motion will stay in motion. So you see, in theory, you could potentially go around the track without using that much energy. I mean, because you have wheels also, right? It's just like, maybe, I don't know if you've ever done this before, but if you ride a bicycle and if it's pretty flat, you may notice that if you just start bicycling and you just start going, you could just kind of keep rolling. And it might not take that much of your energy, but you just keep rolling. On the other hand, if you want to use your bicycle to go and catch another car, oh my gosh, that's not easy. You have to bike like crazy, you have to pedal so hard. And furthermore, as you start pedaling harder, you notice it gets harder to do so. Because there is friction and gravity. Philip Neller, you're right. It's like you can't really go forever with no energy. However, if you're going slowly, you actually don't lose too much energy. You see, because there is friction. But if you have wheels, the wheels don't have that much friction. It's called rolling friction. In fact, even as the wheel is going around, there are things called ball bearings inside the wheel. So there's nothing really scraping surface to surface against another thing. So everything's rolling. But what people just said is air resistance is increasing. This is correct. And so the situation is that as you go faster and faster, you actually have to deal with this aerodynamic drag of the air resistance of all the air you're trying to go through. So the answer to your question is an interesting one. You see, how much gas will it take to go around the track? The answer is it depends how fast you're going. If you're willing to go very slowly, you won't actually use that much gas. If you're trying to go as fast as you can, then you start to use a lot more gas. And now because the answer is something that I don't know, I mean, it depends on how fast you choose to go, the way I would answer this question is, suppose I'm the pit crew. Pit crew meaning I'm the one who's supposed to go and help fuel up the car. The F1 racers, Formula 1 racers, they don't want to overfill with fuel because there's no point just like dragging fuel around. You care about everything. You're trying to win this car race. So what you do is I'll use statistics. I'll go and say, okay, so this particular driver, when they drive around the track, I filled the gas up to this amount, and it looks like they used only this amount of gas. And then what I would do is I would actually just go and take an average. I'd say as this person is going around, how much gas did they use this time? How much gas did they use that time? Actually, I might even be more sophisticated. I might start to draw a graph. I might try to draw a graph which is something like how much time did it take for them to finish the lap versus how much gas did it use, right? Like if I was actually in charge of this pit crew is what I think they call it, like the crew inside the pit, which is trying to help everyone, help the driver go as fast as they can by providing new tires and by providing, by also providing the gas, right? So I'd make this little graph. And the graph would be something like, on this axis, this would be called the lap time. Lap time would be how much time did it take to go all the way around the lap. And the other thing I would put is I would probably put the gas used. So if I have these two different pieces, it's like as I look at these two numbers, I'll start to be able to find some kind of relationship. You see, I would expect that it wouldn't just be always the same amount of gas used. If the lap time was huge, meaning they took forever, they would use less gas because, you see, the situation is that the wind resistance, the air resistance grows as you try to go faster. And so that's actually what you need to fight against. So I would expect that as your time gets more, your gas used goes down. So I would guess it looks something like this. I would draw what's called a scatter plot. I would say, okay, this time you went, and this time your lap time was whatever it was, and your gas used was whatever it was, here's a dot. And I would say, okay, let's do it again. And you do it again, you get another dot. And you do it again, you get another dot. You do it again, you get another dot. And you get all these dots. I actually don't know if it should be a straight line. I didn't think enough about this. I think that if I wanted to do this carefully, I would need to know exactly what happens with regard to the drag you get. I vaguely remember that the drag you get is somehow quadratic in the velocity, but I actually don't know that relationship. Oh, yes, actually, you know what? I know for sure it's not linear. And the reason I know it's not linear is because if you run the lap time to 0, it's not possible to get a 0 lap time with a finite amount of gas. You probably had to just go jam really, really hard. So in that case, I would expect the graph to look more like this. Does this sort of make sense? I just sort of made some kind of a chart. And you would expect that if somehow somebody told you, I can finish the entire race in 1 millisecond, then you're like, wow, you probably used a ton of energy. And in fact, at that point, the energy you're using is not even just the wind resistance. At that point, the physics that you're saying is when you accelerate something so fast, that alone is going to use a lot of energy. Like actually, you use a lot of your gas, just increasing your speed to that kind of a pace. Anyway, so I'd expect something like this. And after I look at something like this, I'll just go and try to trace a line through it and say, here's what I think that you'd use. And then I might go and look at who you're racing against and say, it looks like this time you're racing, you'll probably be trying to get this lap time. Okay, then you'll need that much gas. So that's how I'll answer your question. And hopefully you can see now that the answer to the question actually depends on how fast you're going on the track as well. And that's what statistics is useful for. Okay, more questions. Oh, I saw... Jeffrey Chang asked to Debbie, is Novid out? Well, we're working as hard as we can on that. Hopefully we'll have something soon. Actually, we spent the entire weekend building the iOS version. So we actually now have an Apple version and an Android version. Both of them are getting built at the same time. As of right now, what our team is doing is it's making the Android version and the Apple iOS version talk to each other. And so we actually are hoping that in the next 24 hours, we'll actually submit both of those forward to Apple and to Google, and then we'll see what happens. Okay, what else do we have here? Oh, that's cute. I saw somebody say, how are cereal boxes made? That's actually an interesting, that's a very, very interesting geometry problem. And I don't actually know the answer to cereal boxes, but I'm going to show you something else that's pretty cool. So if you have a wrapping paper and you're trying to wrap a present, what do you do? And this is directly related to your question, because somehow when you make a cereal box, it's a piece of cardboard. And so you want to make the cereal box cut out of cardboard in some efficient way. Does anyone know what's the best way if you have a square wrapping paper, that's the wrapping paper, and you're trying to wrap a package. And maybe the package is it's like a cube or something. I stick the package here. How many of you try to wrap like this? Where you put and this is like the package, okay? This is the package, you just stick the package there. Do you just put it in the middle and kind of do this? Is that what you do? I mean, that's what I used to do. It turns out that there's a better way. That doesn't work too well. Yeah, it doesn't work too well. And also there's a lot of wastage. But, oh wow, somebody here knows this. Is it Jacobo? Jacobo says that you should do diagonal. I didn't know this until very recently, by the way. Do it this way. If you do it this way, you actually can get all the way up to the top. Because you got to think about it. Like, suppose you're trying to wrap a package. Wrap the package means that you get all the way up. And if you try to wrap this way versus the other way was like this. With the other way, if you try to wrap up from both of these sides, what you end up doing is actually you won't get all the way to the top. You can see that here. If you try to wrap it up, you'll be like, yes, you have just wrapped a package where anyone you give the package to can look right down and see what the package is. Does that make sense to people? Like if I'd used this wrapping paper and tried to wrap it up, I'm like, oh gee, I need a bigger piece of wrapping paper because I can see the top. But what happens over here? If you try to do the wrapping on this one, actually, as you start wrapping around, it in fact is just right that as I wrap around from this one coming over and that one going over, this piece will just get to the top of that package. And then what you'll see on top is that somehow the four pieces come together. Does that make sense to people? It's like I'm going to erase the center of this. But as it's coming together on top, what you'll see is you'll almost see like this flap coming in like this. And then the other ones are going around. Did that make sense? It's like it just goes all the way up and it closes. I just saw that our live stream got stuck. Oh, it looks like we're fine again. Are we fine again? Okay, I think we're... Let me see. So I'm actually monitoring this right now to go and make sure that our live stream is still going. But I think it seems okay. I just see a little warning on my computer saying that somehow the OBS studio has disconnected, reconnecting. We'll find out soon. Let's keep going. Okay, so anyway, this is what we have here. And this is about maybe related to cereal boxes. Okay, let's see. What should we do next? More questions. Oh. Ryan Jiang asked, what's your highest alchemist rating? I've actually never done alchemist. I'm sorry. I think it's a pretty cute system, but I just myself never did it. It didn't exist when I was around, so I don't know. But I'm glad that some people find it. I'm glad that people find it useful. Other questions? Ooh, this is interesting. Lu Wu Du asks, what does Bluetooth have to do with math? So I can tell you the fundamentals of why people were using Bluetooth to go and find out how far away other phones were, and it's related to math. The relationship between Bluetooth and math is like this. Suppose you have an antenna. I guess it's Bluetooth, so let's go and make the antenna send blue waves outside. Okay, so you got this antenna. And if you have an antenna and it's sending out waves, it turns out that if you're listening to the waves over here versus twice as far over here, the intensity of the waves is lower out here than it is in the middle. Actually, this entire thing was the topic of one of our daily challenge courses. So, as some of you may know, I run the online daily challenge courses as well, and so this thing here happens to be one of those. So I don't want to go too deep into that because it's already inside the course. But the bottom line is that somehow when you're out here, the signal strength is actually 1/4 of the signal strength over here. It's 1/4. It follows something called the inverse square law. And so since it's 1/4 of the signal strength that's over here, you can actually go and try to figure out how far away you are by trying to measure what the signal strength is. So a lot of other people who are using Bluetooth to try to figure out how far away other phones are, what they're doing is they're saying, well, if only I knew what the signal strength would be if I'm standing here. Now, they measure that. They measure that distance. They measure that strength. And then what they do is they say, okay, now I'm standing somewhere else. Oh, and my signal strength is something. You're able to read that in your phone. And they use that to estimate how far away they are. And that uses the inverse square law. So in fact, the whole heart of trying to figure out how far away something is using Bluetooth signal strength is all based on something called the inverse square law. It's related to the function 1/x². So yeah, so the Bluetooth is directly related to math. Although we ourselves don't use that. The reason we don't use that is because this is just fine. But if you got some like giant person standing in between, then suddenly your signal strength becomes wrong. Because somehow that person is blocking too much of the signal. It gets even worse if it's a giant person carrying a big metal plate. Then unfortunately nothing happens at all. Of course, the real question is like, how did that giant person get there in the first place? I guess that would be the topic of another joke. Okay, let's see. What else can we do? Other questions. Oh my goodness. Oh, come on. Epic Paradox Justin Wan wants to know, how do I use your dice game against friends? Come on. You don't want to use things against people, and furthermore, they won't be your friends anymore. No, okay, so the dice thing, like, please use responsibly. Some of you know I've been running around the world telling people how to roll dice more efficiently or how not to get cheated. If you're curious about that, I think if you look on our YouTube, you might even be able to find some talks recorded where I'm talking about this dice game. But I would recommend don't use things against your friends. Instead, what I would recommend is, talk to your friends and see if you guys can together find a really nifty trick that uses dice or that uses anything. And you should understand the world is so broad, there's so many different things you can do that you might be able to find things that other people never thought of before. That's the most fun, by the way. It's the most fun to creatively come up with something that you sort of feel like you own. And it doesn't have to be that you're the only person in the world who did it. It doesn't have to be that you're the first person in the world who did it. That's how I learned math. When I was learning math and learning about anything in physics or whatever, I would actually try to own it myself. I would try to go and think about it, understand for myself with my own explanation of why this works, and then I would feel, quite proud. It's like, now I figured it out for myself. And it also stuck. Okay, more questions. Oh my goodness, who's impersonating me? So somebody named Po-Shen Loh said, how do we protect our computers from the coronavirus? So this is quite funny, actually. As we were writing our Novid app, we realized that we were actually writing an antivirus program. And I mean, but it's a real virus. But I guess that's not really a laughing matter either. So it's like somehow, yes, there are real viruses that hurt people. There are computer viruses which are different. how to protect your computer against the coronavirus, here's what I would say. There is something that is a problem right now that is fooling people, which is that some people are using disasters like the coronavirus to go and fool people, to go and say, hey, I have a cure, and all you have to do is pay me like this amount of money and I'll cure you of it. And maybe they try to reach out to you from your computer. Or they maybe try to tell you something like a flash something on the screen saying, we just detected with your webcam that you have a fever. Call this number right now and we've got medicine for you. I mean, this is, yes, exactly. Austin, you're absolutely right. This is phishing. Phishing with a P. And this is not a joke. I mean, like, a real problem is that whenever there's an issue like this, where people are scared of something, people do take advantage of them. So what I'll give the advice to you is, there is no way your computer can tell if you're sick, unless you have some really special app. But even then, I'm like, how would your computer take your temperature? You know what I mean? So it's just like, please be careful of any kind of things like that. Actually, recently, last year, I got all these calls of people saying, we are the government, and we realized that you did something wrong with your taxes. You owe us $10,000. Call this number right away. And they try to sound very official. So be careful of all these things. Okay, let's see. What else do we have here? Oh, this is cute. Andrew Chow, you asked a question that's kind of like philosophical. You said, here's a number called 10. And in 10, which digit is more important? Is the 1 important? Because the 1 is nothing without the 0. If there's no 0 there, doesn't mean anything. But so that means that the 0 is really important. But if you just have the 0, then you also don't know either. And then somehow you need the 1. So here's what I would say. That particular question that you gave, both are important. Both of the numbers are important. But let me say a few more questions. Suppose what I told you is not 10. Suppose I told you 12715. That's a number. Now, how important is each of those digits? Oh, let me be more confused. Let me be more like more numbers. 9, 6, 9, 0, 1, 5. Okay. Now I wrote down a lot of numbers. Suppose someone told you that this was the population of, like, what kind of a country? Oh, so that's, wow, this is 1 billion. So I'd say, what if someone told you this is the population of some country with 1 billion people? You know, like, maybe this was the population of India or China sometime long ago. Okay? Maybe not that long ago even. But somebody told you, here, that's a number, population. Do you need to remember all those numbers? Of course not. Like, who cares about the 5? If that's the population of a country, there's going to be people born all the time. It's like, who cares about the 5, right? And so, yeah, maybe China, maybe India, maybe some other country at some point. But I'm simply saying, here's a very long list of numbers, and which of those numbers are the most important? Well, actually, the most important thing is how many digits are there? Right? Remember, like, when I looked at the number, I was like, hang on a second. Is this like the population of Spain? Or is this like the population of the United States? Or is this like the population of China? You know what I mean? It's like, what order of magnitude are we talking about? The important part of this number is that it is roughly 10 to the power 9. And that's because, you know, like, that's, let me make sure. I'm going to draw some commas. Comma, comma, comma. Excellent. So the important thing is it's about 10 to the power 9. And so the most important thing in this number is 9, which, by the way, is one of those digits. But that's not what we were thinking about. So the main thing is, it's just like somehow what's important about a number. Generally speaking, it's like how big it is. Roughly speaking, how big it is. And this is the 1, right? So it's like really like there's a 1, a 0, and a 9, right? But what's important is it's like there are 9 digits after the decimal point, so to speak. Sorry, not digits after the decimal point. There are like 9 powers of 10. That's what's going on here. Okay, let's see. So what else can we see here? What other questions do we have? Oh, this is cute. So there's a question about from Sophie Zhang. Sophie Zhang asks, how is math used in sports? Now, I don't know if you guys found this, but there's a video of me on YouTube. It's called Coach Po Talks Math. Has anyone watched this video? This is about like football, American football. I don't know if everyone here is from America or not. Probably not, actually. Has anyone seen this, like Coach Po Talks Math? So this is about the best way to run in football. You saw the thumbnail. Very good. So I'm going to tell you, if you're playing football, you actually can use geometry to go and find the best way in order to run. Oh, it looks like somebody watched the cheerleading one. That's awesome. So we have all of these different videos which are involving football, involving cheerleading, and all of these things use math in certain ways. I don't want to restate it. That's why I'm just telling you there are these videos. They were already made. They're pretty fun. They're pretty awesome, right? Go and look at those. And what you'll find out is that when a mathematician, or when you, while you know math, look at a general problem, you will be able to go and figure out what is the best way to do each of these sports that you want to do. Actually, sports is just about physics. And if you can control the physics, you can actually control winning. How do you understand the physics? You understand the physics by understanding the math behind it. And sometimes when you think about everything with math, you actually get better strategies. Somebody asked, why am I drinking water? The reason is because I actually have been paying attention to how COVID-19 spreads. And some of the studies of how COVID-19 spreads is that at some point it can go down your throat into your lungs. By the way, I don't think I have COVID-19, but the advice I heard is during this time, it's the best to keep your mouth as moist, not as moist as possible, but make sure your throat doesn't dry out, because that makes you less susceptible. This may or may not actually be true, it may or may not actually be effective, but I'll do it anyway. It doesn't hurt me anything to drink some more water. Okay, what else do we have here? Eric F has asked a question about Eric F asked a question about square root of 6 plus square root of 6 and so on. These are cool questions. I won't hit it here mainly because it's already actually in one of my online courses. So, but I'll say this is something where it's a fun equation, and yeah, I throw it here to encourage anyone who wants to play with this. It's good. Let me see if I can hit something else that's not in any of the classes and maybe not in the class that you'd see anyway. I always try to make these live streams something that is different. Paperboy asks, what is 1 plus 1? That's 2 by definition. Somehow, when you say what is 2, 2 is 1 plus 1, and that's just a definition. But I think I also already talked about some of those topics here in previous live streams too. Huh. Oh, somebody said 1 plus 1 is 11. Somehow, there unfortunately isn't any base that makes that thing actually work. When I say any base, it's like sometimes you can say, oh, I was just in a different base. Right, what is 2 plus 2? We did talk about this thing before in another live stream actually, so I won't hit that here. Oh, that's interesting. So somebody asked, what's the probability of COVID-19 still going on by 2021? Now that's a question that I care a lot about. For many reasons. One is that I do teach. I teach at a university. And so from my point of view, it would be really nice if our students could come back soon. Now, if you think about what is causing us to not be safe, right? Why are we not safe? The reason we're not safe is because too many people can get the virus still. And so COVID-19 will be around until either a lot of people got the virus, like 60% of the people got the virus, or until we get a vaccine. And there are people who are working as hard as they can on the vaccine right now. Unfortunately, with the ways things are going, it actually doesn't look like we'll get the vaccine until 2021. So if you asked me, my analysis right now is that the probability we'll still be having this COVID-19 in 2021 is quite high. I wouldn't be surprised if the probability is like over 50%. And so consequently, I'll go and organize my life so that I can survive through that as much as I can. That's also why I'm running these live streams. These live streams with all of these people chatting here on the chat. And also that's why I keep saying, hey, make sure you bring more people. If you bring more people, these things are worth a lot more, because then hopefully they can touch more people. Okay, what else do we have here? Okay, this is neat. So Sentinel asks, are there people who simultaneously calculate the physics of sports while committing to it? Is it physically possible to do both at the same time while still being able to concentrate? I think actually you raise a good point. It's like if I'm playing ping pong, sometimes I'm not thinking about the physics as I'm going. In fact, I'm never thinking about the physics as I'm going. However, when I'm designing my shot, right, I'll actually think of different shots I might do. And while I'm planning the shot out and trying to say, let me go and rehearse and practice this thing, I first go and make sure it makes sense from the physics perspective. So any move that I'm going to make, at some point it has to become muscle memory. And before that point, it has to be something that obeys the laws of physics. So I go and think of what's something super cool to do, then train it, and then go. But the reason why you need to train it is because actually there's not enough time for the signal of like your nerves to even get to your brain and back. Like a lot of these things have to be somehow already pre-programmed to go. And the best example is that somehow so I like playing ping pong, if you want to spin something, you basically need to contact the ball for a split second. As it's coming to you super fast, you need to do this, and your body needs to already know the motions where basically the nerve tells something here almost that it's gotten contact, or tells something at the base of your brain that you got contact with the ball. And then with that, it immediately makes some adjustment. No time to think. So I'll simply say that I think that the actual motions you go through, once you actually do them, you aren't going to be thinking about the math necessarily, but you'll think about the math beforehand. And that's also how when people prepare for American football, a lot of the time, the people who come up with the strategies of who's going to run where, they're thinking about all the geometry, and they plan it all out, and then the people practice it all out. Okay. So I saw there's a question by Philip Neller asking about what's the square root of I. So this is interesting, because you were asking, you know that the square root of -1 is equal to I. That seems reasonable. And now your question, no, sorry, that doesn't seem reasonable at all. That's not reasonable. That's just the definition. And that's not reasonable to many people because somehow you shouldn't be able to square root a negative number anyway. But what happens with the square root of I? Okay. Now I'm going to tell you something that you will probably not be happy with because you'll be like, where did that come from? But here's what I'm going to say. It is 1 over the square root of 2 plus 1 over the square root of 2 times I. Some of you here will say, he didn't rationalize the denominator. It should be root 2 over 2 plus root 2 over 2 times I. And you're right. However, I'm just telling you a number. And if I read it like this, that's still a number. Watch, it works. How? How is the question? Well, let's first see that it works. And then you'll be like, how did you get it, right? Like you can't just like write down something like this without thinking. So let's check. I have to multiply it by itself. 1 over root 2 plus 1 over root 2 I. Okay, so let's multiply times itself. 1 over root 2 plus 1 over root 2 times I. Okay, so if that's the case, if I start to combine, I have a 1 over root 2 times a 1 over root 2. That's a 1/2. Then I'm going to have 1 over root 2 times 1 over root 2. Wait a second. Is that right? Just a second. I'm trying to think. Well, let's see. I hope it works. So 1 over root 2 times 1 over root 2 times I. Actually, it will work. That's going to be I over 2. Then I have 1 over root 2I times 1 over root 2. That's 1 over 2I. I mean, half I. And then the last part is 1 over root 2I times 1 over root 2I. Aha. That's 1 over root 2 times 1 over root 2. But I write minus 1/2 because the I times I is -1. Did that make sense to people? I just went and took like the FOIL. In America, we call it FOIL. The first terms multiply to this. The outer terms multiply to this. The inner terms multiply to this. And the last terms multiply to this. And I times I is -1. Okay. So if I go put this together, fortunately, I get canceling. Look, it works. Wow. And there's also another choice. The other choice is also negative of that. I mean, somehow, actually, what's not quite well defined is the square root sign around an I. The square root sign always talks about the positive square root. It's not clear to me that this is the positive square root or that the other one is the positive square root. So I'll tell you this. When I write a plus or minus here, this is equal to plus or minus this. And what I mean by that is that if I took minus of this, like minus 1 over root 2, minus 1 over root 2I, and then multiply it by itself, I would also get I. Okay? So somehow the positive and negative roots are exactly positive and negative of that. Now why? The deep question was why? And that is something that goes into trigonometry. That's something that's related to this e to the power of pi times I. But I can just show you a pattern. And if I show you a pattern, it will be something for people who are taking algebra or geometry. Next time, if you ever get a question like this, you might be able to just figure out the answer. This is cool. Yes, Philip, let me show you something even more cool. All right? Here. this is how we draw complex numbers. What we do is if we want to draw -1, I should say what these are called. This is called the real axis, and this is called the imaginary axis. So the way we graph our complex numbers is we say -1 is where I write -1 on the real axis. I go with -1, and that, let me not write it so far, that is -1. So this is -1. Now I also want to tell you where I is. I'm looking at the first thing. I is where you go up the imaginary axis by 1. I want to show you something very interesting. This is -1, that's I. There's something else, which is the square root of I, and the square root of I was somewhere over here. In fact, that place that it was over there is 1 over root 2 and 1 over root 2. In fact, it's around here. Square root of I, and in fact, maybe I don't want to write it as square root of I, because as I said, it's not clear which is the positive and which is the negative. I'll call that 1 over root 2 plus 1 over root 2 I. Okay, and this particular point is where I went 1 over root 2 over and 1 over root 2 up. Now look at this. Here's I, and here's -1. I want you to compare these two angles. The angle to I and the angle to -1. How do those two angles compare? I is like 1, but imaginary, yes. But how do these two angles compare? This is the -1, and this is the sort of square root of it. Another way to think of it is this is the I, and this is the I squared. How do the half? Thank you, Lily, you're right, they're half. And why did I say to compare angles and talk about half? Oh, look at this. You asked me to find what happens when I want to find the square root of I. So in fact, what I did is I thought about this. I was like, okay, so the I is at 90 degrees. If I go all the way over, that's 90 degrees. And the answer turns out that you need to go half of the angle measure. So if I was able to draw where this is half of that angle. And the proof of why this is true requires some work in trigonometry or algebra 2. But ultimately, if you want to find the square root of a complex number, you actually just take whatever angle it makes with this particular real axis, the positive rail, and I take half of that angle. You also have to do something special with how far along you're going. That's called the magnitude of the complex number. It's related to the absolute value. It's like the absolute value of -1 is 1, and that's because the distance from -1 to the center is 0. And the absolute value of I is also 1 for that reason. Absolute value is like how far away. Aha, yes. So I see that Lily Ma asks seriously. I'm not entirely sure if you're saying seriously to me or seriously to other people, but I do believe that that sort of thing I just said does deserve someone to say seriously. It's like somehow, it's amazing. You actually, if you want to take the square root or take a square of some number in the complex, some complex number, the easiest way is to draw it. And then the angle, when you take a square root, you half the angle. And if you square, you double the angle. And if you want to know what to do with the absolute value or the magnitude, actually, if the magnitude was 1 to begin with, the magnitude is the same. Otherwise, what you need to do is you also need to take the square root of the magnitude or the square of the magnitude. That would be the topic of another thing. But Joshua Wang says that is amazing. I'm glad you find that amazing because it demystifies this topic. It's like, at first you're like, how would you ever find that in your head? Well, the way you'd find that in your head is you go and say, I want to draw like half of that angle, and I want to take the magnitude it was before and get the square root of the magnitude now. And it becomes almost like a right triangle geometry problem. Okay, this is a topic of Algebra 2. I think you'll enjoy it whenever you go and learn that one eventually too. Let's see, what do we have here? We've got a lot of green shirts. Oh, okay. I'll finish with this one. This is like a soft question. So, yeah. So Yo-Yo, actually, you know what? This is not soft question. I'm going to take a hard question because I think you deserve it. So Yo-Yo says, I want to get this straight. So yeah, this is a legit serious question. Let me hit it. Yo-Yo Kojo says, how can I get over the pain of being 20 days too old for IMO, even though I made my country's requirements to join? Right. So here's what I'd say to you. first of all, congratulations. That's an extremely, extremely huge accomplishment. But you know, the IMO at a certain point in your life, at a certain point in your life, is like the most important thing in the world. There's a reason why the IMO kind of cuts off at 20 years old. And the reason is because you have much, much more in front of you than you had behind you. I think that the thing that you should feel is like you have managed to distinguish yourself in achieving something at a national level. And by doing that, that's something that gives you a lot of strength to say, in the future, if I'm ever going to do something hard, I have done something very hard before, so I can do it in the future. But there's a reason why they cut off at 20 years old. It's because at that point, you should really be looking forward to say, where should I be going next? You know, it's like those are things that you do younger, earlier in your life. At that point in your life, you basically solve problems that other people tell you to solve. The interesting part of life is when you yourself decide what problems you want to solve, what problems that you see in mathematics, in science, or in the entire world. And then you go and say, now I'm going to try to solve those. So to get over the disappointment of like, oh my gosh, you're just like, just slightly too old for the IMO, don't worry. I mean, it's okay. That's life. Actually, I think right now there's a lot of people in this United States, for example, who are very disappointed that it's like they practiced so hard for math counts and they're in 8th grade and it was the last chance and there's no more math counts. Well, you know what? The good thing is that in your life in the future, it won't matter anyway. It's like nobody will remember what you actually did at those ages. You don't care what I did when I was at that age. That's completely irrelevant. On the other hand, the fact that I did those things earlier on make it so that when I face a question today or I face a challenge, I don't know, like, can you do anything in this? What I was interested in is, can you do anything in this world with everyone suffering from COVID-19? Can we do anything? Well, if you've done something before, you're willing to go and try. And I hope that you'll have that same thing. And so someday in your life, you won't be worrying so much about whether or not, you got to the IMO at this age. Hopefully you'll be thinking about what other things that you can do. So I encourage you, look forward to it, be proud of what you've done. And this applies to everyone else who had their math competitions canceled. Don't worry, be proud of what you've done. And I can guarantee you, just based on my own experience, all the stuff you did is really, really useful if someday you actually want to use it for a real, serious world problem. Okay. Well, that wasn't the light ending, but I think that you deserved it. I mean, given the strength of the comment, I wanted to make sure I addressed that. So in any case, I wish everyone a good Monday. I myself am going to go back, and we're trying to figure out how we can get the Novid app into the Apple and Google app stores. Hopefully, we'll have good news soon. But I wish you all the rest of the day. I wish you all a good rest of the day, and I'll see you tomorrow. See you.